Thank you very much. I'm very happy to be here, and thank you, Victor and Ivan and the rest of the organizers for inviting me here. I'm very happy to reconnect with the greater computer vision community in Russia. So, because we have already seen a lot of heavy math, this is going to be a light talk. This is going to be a dessert. So. Hopefully it will be, and thank you to Victor, who already introduced a lot of the formulations. I skip all the equations, so it will be just pictures, okay? And of course, the work is really done by my wonderful group at Berkeley, the students and postdocs who are really amazing. So. Life is good in deep land. I'm sure you have heard of the deep network revolution, and it's almost like you don't need to design algorithms anymore, right? You basically just, for any given problem, you label some training data, define a cost function, and train neural network, and then you sell your startup for millions of dollars, right? Of course, it's not so simple because these two steps, the labeling the data and the defining the cost function, they're actually very difficult. Labeling data is expensive. You have to have people clicking on millions and millions of images because networks are data hungry. And also the objective functions are finicky. Objective functions, of course, are what you want the network to do, and usually they're designed by hand. And here, it's important to avoid the mistake of King Midas. If you remember your Greek mythology, King Midas, he wanted to optimize getting lots of money, and so he asked. His loss function was make everything I touch turn into gold. So it turned out this was not a very good loss function because he couldn't eat, he couldn't, he killed his wife by touching her, and so, it didn't end up well. And so whenever you're trying to tell, what you want, it's very important to be really sure that that's what you actually want. Otherwise, the network will just do it and you will not be happy, okay? And so in my research group, basically what we're trying to do is tricking the computer into doing a lot of this hard work by itself, okay? And I'll just give you a bunch of different examples. So first is this idea of self-supervision. And self-supervision, so there is unsupervised learning, there is supervised learning, and this is kind of in between. And basically, it's using supervised methods, but using the data as its own supervision, okay? And we actually, most of you guys probably, how many people have heard of word-to-vec in text? Word-to-vec? Okay, a lot of people. So just very briefly, what you want is you want to have a vector representation for a word. What do? You get a huge text corpus, and then you randomly pick a phrase, then you take one word from that phrase, and then you train a network or train some kind of a model to predict the words that are likely to occur within the context of that word. And so you do this task. This is not a very useful task, but the interesting thing is you do this task over and over and over again, and you get a representation that turns out to work very, very well for a lot of language problems. And this is an example of self-supervised learning because you don't have to label any data. The data is just random text. You don't have to have any labels. It's only the data. And so our idea was to see if we can do something similar in the visual domain. This is work of Carl Dorch and company. So here's the idea. We take an image and we take two patches from it, patch A and patch B. And then we want to solve this completely useless pretext task. Given patch A, where should patch B go? And now I want you guys to pretend you're a computer and to see if you can solve this task. Where should the patch B go? Down and and to the right. Very good. Very good. Now, try to introspect a little bit. In psychology, you're not allowed to introspect, but here it's okay. How did you solve this problem? Exactly. You thought, well, this looks like the top of the bus, this looks like the bottom of the bus, and once I connect it to other buses that I have seen before, okay, now it's simple. Now imagine that you come from some island where you have never seen buses in your entire life. Would you be able to solve this problem? Probably not. And so the idea is the following. We're going to force the computer to solve this completely useless problem, and by doing it, the hope is that it will have to figure out what a bus is. So we will try to learn semantics by doing this kind of prediction problem. And that's what we do. We take tons and tons of images. For every image we pick a patch, then we pick a set of 8 other patches, and then for any pair of patches we set up a kind of a classic Siamese network, and then at the top of the network is a standard 8-weight classifier. Okay? And then we train this thing for 5 weeks. Okay? This is a hard problem. It's the loss keeps going down even after 5 weeks. Okay? And then, of course, the interesting thing is, what has it learned? So what we can do is we can, at test time, give it a new patch, and then look at the top level of the representation, the embedding, and see if that embedding is meaningful, interesting. And the simplest way to do it is to look at nearest neighbors. Look at what are the closest other patches in a big data set to that query input patch. And the cool thing is you can see that the other nearest neighbors are also cats, right? Even though at training time, we only trained one image at a time. We never made it look across images, and yet it basically discovered automatically correspondence across instances without any supervision, right? So it's a little bit magic, right? Using context, you discover these correspondences. And so that got us really interested in this idea of finding correspondences and finding good embeddings without supervision. And of course, this is representation learning has a long history, and there are probably faster ways of doing this. You take an image and you basically want to reproduce some sort of a code for that image, hopefully a low-dimensional code, and that's your representation. So it's kind of like image to vec, right? And the most classical way of doing it is, of course, an autoencoder with your loss being a reconstruction loss. You just basically want to reconstruct exactly the same image you got in. Okay? Now, this is, of course, very famous, works, everybody knows about it. What most people don't realize is that actually for real data sets, for real images, it doesn't actually work very well. It's not, and other things like a denoising autoencoder also don't work very well. And the reason we think is because this is basically a data compression story. And there is a connection between compression and machine learning, but it's not an exact connection. Because for compression, you really don't care about the test set. You really only need to compress the things you're compressing, the training set. Whereas in machine learning, it's really all about what you're going to do at the test time. And so what we proposed is to think of this, make the computer work harder. And instead of just compression, can we think of it as a prediction problem? And so one way to do this is you take your input data, split it in half, and you try to predict the second half from the first half. Okay? And the most classical way of doing this, for example, would be colorization, right? So you take a color image and you split it into a chrominance, a luminance, and then you try, given luminance, to predict chrominance, right? And the nice thing is, once you do that, you get a pretty picture out all, right? But the more important thing is to, hopefully, you also learn some good representation in the middle, okay? But of course, once you have good pictures, you want to show the good pictures. So we have Ansel Adams, Yosemite. If people want to go to west of the US, it's beautiful. Some other historic images. There are some failures. The hair is definitely not orange enough. There is more instructive failures. Anyone can tell me what are the failures here? There's a more obvious failure. Here, I will flip it again. No? The tongue. The tongue is not actually out, and yet it colored it red. So you think, why would it do that? Well, because we trained on ImageNet data, and in ImageNet data, all the poodles, for some reason, have their tongues out. So this is actually very good news, because what this means is that it's not some low-level colorization thing. It's actually recognize that this is a poodle, and then try to color it the way poodles are colored. So again, without any pre-training, without any supervision, we're getting something that is kind of getting us to semantics. So we can do some, deep net electrophysiology, pick a neuron, and then display, what it fires on. And so these are some nice neurons that the graduate students found. Not all of them are like this, but there are some that definitely suggest that there is something that might be going on. But of course, you can't really use this as a representation yet, because remember we split the input data into halves, right? So the representation has only been learned on a half of the data on the grayscale. What about the other half? So what we do is we basically do exactly the same thing, but in the reverse, and try to predict from color to grayscale. And then if you look at it, if you squint a little bit, that's kind of like an autoencoder, right? It's the representation takes an image and predicts an image, but it has to work much, much harder to do this task. And so hopefully it also works better. Okay, so this is our CPR 817 paper. We call it split brain autoencoder. And we can. I didn't actually explain how we're going to look at it. There are numbers in the paper. We're basically going to look at how effective it is at predicting ImageNet results by just a little bit of fine-tuning. And so here are the comparison between split brain and autoencoder, and you can see that autoencoder basically starts overfitting as it goes up the network, and the split brain doesn't. This very simple approach seemed to work quite a bit better than a lot of other self-supervised algorithms, but of course it's still not beating the supervised method, which actually uses the ImageNet labels in addition to the ImageNet data. But the hope is that because it's unsupervised, you can use orders of magnitude more data, and so hopefully eventually we will beat them as well. But this is definitely still a work in progress. Okay, so the second thing though is whenever you talk about predictions, you have this question of how do you evaluate your predictions. And evaluating predictions in a one dimension, a low dimension, is not that hard. But if you want to evaluate predictions in terms of pixels, it becomes actually quite a bit harder, right? So here, this is what we are trying to optimize, right? We are trying to find f such that we minimize the loss function. So we say whatever the f of x should be as close as possible to your label y under some kind of loss, right? And the loss is standard, the standard loss would be something like L2 distance, right? Well, the problem is that L2 loss is not a great loss for these kind of problems. And I will show you an example. So here is what happens if you do colorization with an L2 loss. It looks kind of grayish sepia kind of thing, right? Compared to the ground truth. So why is that? Well, it's actually very simple to see. It's actually connected to the problems that Victor has talked about and Jiří also. It's L2 really assumes that you have a single bump, a single mode. But what if you have two modes? Let's see, this bird could be blue or it could be red. What would L2 want to do? It wants to split the difference. So it's going to do the average of those two, which is going to be right in the middle where all the gray colors live, so it's going to make you gray. And so a lot of the time when you're using L2, you're basically getting either this kind of gray thing, or in other examples you get blurry results. Again, because it's trying to make everyone happy and basically look at the average. And L1 is a little bit better for reasons that Jean has talked about, but it still doesn't quite solve the problem. And so what we had to do for that algorithm was to do complicated, change it from classification from regression to classification, and then introduce some boosting to kind of boost the rare colors. It was a lot of hacking by the grad student, but in the end, we got something that looks reasonably good, even though it's actually quite different from the ground truth. So it's kind of producing a different mode, if you want. Now, every time you have something that's done by hacking, you think it's a good idea, and then you run it on a new image and it doesn't work. So in this image, for example, the same algorithm, it knows it needs to be very colorful, so it gives you all these colors in the image, even though we would probably better want the back wall to be just white, right? So it's overshooting. And so again, this is the issue with kick binders. You have to be very careful what you're wishing for. And so it would be very nice if we could have some sort of like a universal loss for any kind of this image-to-image, we call it image-to-image translation problems, colorization, super resolution, whatever. If we could just have some loss that would work for all of them. Well, we know one loss that works very well. In fact, that's the loss that everybody has been using. It's called graduate student descent. The graduate student iterates until the pictures look good. Now, that, of course, is hard to operationalize. And so another loss that actually we have been using was somewhat similar, and we were using it for colorization to evaluate our results. We gave the results to humans, and we asked the humans. We gave them a picture, say, is this a real image, or is this an image that has been synthesized, colorized? And then if the humans cannot tell the difference, that means our algorithm is working very well. But this is, of course, also very expensive, because you need to go to Amazon Mechanical Turk, and then you have to pay money, and it takes a long time. And it's also, you cannot backpropagate through the users, right? And so this is only for evaluation. But luckily, this same loss can actually be operationalized, and this is the seminal paper by Ian Goodfellow and company that Victor has already presented in the morning. That really is actually the perfect thing for any kind of synthesis, graphics problems. It's exactly doing this. It's basically puts in a classifier on top of your result, and it's basically say, can you tell the difference between the image that was synthesized and some other sample from a distribution of images? Okay? So I'm not going to, I skip all this on all the equations because Vito already showed beautiful explanations. But what he was talking about is the kind of the classic GANs, which are general adversarial networks. You start with a random vector, and you're generating images from scratch, so to speak. And this is actually, it's a very hard problem, and I'm great. It's great that so many people are trying to work on it. But what we're going to do is actually solve a much simpler problem called conditional GANs, right? Because we already have some image, and we just want to translate it into some other representation. Turns out that this is a much simpler way of working. A lot of the issues that are so hard become easier in this setting. And again, it's basically, we have our generator. Now we call it G instead of F, because G sounds like a generator. So we have a generator G that goes and transfers from, let's say, color from grayscale to color. And then on top of it, we add a discriminator, another network. And that network is going to say, is it real or is it fake? Okay? And so G tries to synthesize fake images that fool D, while D is trying to detect those fakes. And then you're basically just trying to get those two guys to compete with each other, and hopefully good things come out. Okay? Now, I skip all the equations, but I want to point out that a conditional GAN has a very nice interpretation that is often people kind of don't quite see right away. Basically, from G's perspective, D is the loss function, right? It's a learned loss function. It's instead of like L1 or L2, it's a loss function that has been learned specifically for G, okay? And the nice thing is that that loss function is not, it could be global. It can look at the entire image. It doesn't have to look pixel by pixel. And so I really like this interpretations of GANs, that it's basically just providing you a trained loss function. So now you don't need to pick up a loss function by yourself. You can let the computer do it for you, for a class of problems. And so we, of course, tried it for the colorization problem, and right out of the box, it just produced some reasonable results. So we were very happy with that. But then we thought, we can put any other data in it as well. So my postdoc Phil Isola downloaded maps from Google and also satellite images. And then we said, can we predict what a satellite would look like from this map? And there is a result. And it, again, right out of the box, we didn't change anything in the software. This is the ground truth, so you can see that it's a little bit not quite sharp enough, but it gets the story. And of course, you can do it the other way as well. We can start with a satellite and see if it can predict the output as a map, and that's perhaps more useful direction. We also can do other data sets. For example, this is the facade data set from Zurich, I think, where they labeled for European facades, they labeled things like balconies and windows and doors and stuff like this. And so we say, can you translate from here to an image, right? So given this, can we fake a hallucinated image? And this is the result. And it's not completely realistic. The discriminator definitely still wins. In GANs, discriminators basically always win, but it's getting there. So here is some more examples of these results, and you can look at it and say, wow, this looks so much better than your standard GAN outputs. But again, a lot of it is because this is a conditional setting, so it doesn't need to generate anything in the world. It just needs to generate something that corresponds to this label mask. And even though the label mask is reasonably sparse, it makes the problem much, much simpler. We can turn day into night. We can take edges and hallucinate images. So this is kind of canny edges, and these are the images that it hallucinated. Now, this is maybe not that impressive because canny edges have a lot of information, but then we trained on this, and we tested it on human sketches from James Hayes' data set. So these are like kids drawing sketches, and it's still doing something reasonable, which is, I was very surprised because I thought that this was a very hard task, but it's still able to do something reasonable. But of course it fails sometimes, although it's nice to look at failures too. And the more interesting thing is that we posted the paper on arXiv, and we also put it on the code on GitHub right away. And within a few weeks, magically, all these people started using the code and doing other things with it. So somebody basically tried to predict depth from images. But the more interesting things are these other people who are not even computer scientists. They're artists. They're artists who somehow got hold of a NVIDIA GPU, and they're doing all these really cool demos. So we call it Twitter-driven research, because they would just do things and post them on Twitter, and then we just steal those pictures and put them in my presentation. So it's wonderful. You don't even need to work at all. There was another cute little demo that somebody wrote that basically allows you to interactively sketch cats. And so people went a little bit crazy on this, but this is basically what you can do. You can search for edges to cats, and you can try it yourself and see how it works. It's okay. Somehow the internet really liked this, and just this week, somebody did the same thing for faces, and I even got Jan LeCun to do one for me for this talk. And I'm not sure it's a self-portrait. It's a little bit too thin, but there it is. So far we have talked about doing this image-to-image translation when you have paired training examples. So you had your sketches and then you have your corresponding bags. But there are often cases when you don't have correspondences. Let's say that you have a whole bunch of photos that I took and then a whole bunch of paintings of Cézanne, maybe all the paintings of Cézanne. There are not that many. And can we somehow do the same translation but without the training correspondences? And so in a way what we want here then is we want this kind of setup. We want to have a generator G that goes from some instance in domain 1 to something in domain 2, right? So in domain Y, we don't have to enforce what it is in domain Y. It just needs to be something that the discriminator agrees is in domain Y. Okay? Now this is a very, very beautiful desire, but this maybe is a little bit too much to ask, because I can have G just always spit out the same Cézanne painting all the time, and D will be perfectly happy and everything will be fine, right? So we need a little bit more supervision here, but we don't want to use humans. So what do? Well, the idea is we are going to enforce a cycle consistency. So we are going to say that we are going to train another translator, F, that is going to go the other way, and then we want them to agree with each other. So how do we do this? So this is a cycle consistency loss that we've been working for a few years, and finally we found something that it really works well on. And the idea here is that we basically set up for any instance in domain X, we basically translate it into domain Y. It goes somewhere, we don't know where, it's just that we know that it's in domain Y. And then we apply F to see where it lands back in domain X. And there we know that it needs to be close to the original X. So X hat should be close to X if we want it to be cycle consistent. And we do it the same way the other direction. Okay? And so now this difference between X and X hat is the loss we're trying to minimize. Okay? Now again, if you squint a little bit and you look at these things, they're basically autoencoders, right? Each one is an autoencoder with this discriminative supervision in the middle. So it's an autoencoder where the middle of the autoencoder is forced to be in the other domain. Okay, so it's actually very connected to all of that type of work. Okay, so how do we work? So here is a couple of pictures I took in Paris, and let's see if we can convert them to Cézanne. And here they are. And this is something that people have seen before. This kind of artistic filters, Prisma, for example. I like to think that this is what we are doing a better Cézanne than other people. I particularly point to the clouds. I'm very fond of those clouds. Probably it's because we are able to use all of the Cézannes, not just a single image like standard stylization work. But people have done this before. What people haven't really been able to do before is go the other way around. So here is a couple of Monets, and this is trying to make it into a photo. Okay, and it's a little bit hard to see, which maybe is a good thing because there are still some artifacts. But this is something that we thought was quite neat. Now, of course, to make this talk very nice, I would have shown you some Cézannes instead of Monets, but Cézanne doesn't work as well. So there's definitely still things to be improved. But if you look at it a little bit zoomed in, so you can see that the water, it really seems to get pretty well. The sky, it often gets quite well. The trees are still a work in progress. So you can see that if you zoom into different parts of the image, you can see that often you get things that, wow, this looks real. But then you look at the full thing, it's like, no, not quite. So I think there's still work to be done here, but I think it's exciting. So we can also do other, Van Gogh and some Japanese stuff. So this is, you can just run wild with your own photos. All the cycle GAN is also on GitHub. You can download it and play with it right away. We applied it to other things. So for example, computer-generated images to real images. You want to have your Yandex driving car. You don't want to train it on Moscow streets. You want to train it in simulation. You take Google, the Grand Theft Auto as your simulator, but then you apply it to real images. Doesn't look so good. It looks very different, so it doesn't work so well. And so this is what happens if we transfer it using CycleGAN. And it's again not quite there, and but we're able to get much better performance than just using standard training with standard Grand Theft Auto. And just for fun, we also did it the other way around, and that looks kind of funny. We can also do changes of season, summer to winter, and then winter to summer. We can do turn oranges into apples, and then back again. We can take horses and turn them into zebras, and the other way around. Notice that the background also changed, and that's to be expected because it never was told what a zebra is. So because zebras hang out mostly in Africa, it's warmer, so everything looks more yellow. It also kind of realizes that the background needs to be more yellow when it's a zebra than it's a horse. We also run it in a video, basically just one image at a time, no continuity at all, and it seems to work reasonably well, although you can see that the stripes are kind of sliding a little bit. But this is basically no spatial continuity at all. And even the failure cases are kind of funny. So, so let's see. I have just a little bit of time left, so I'm going to give you a little teaser of another work that just came out that is also trying to use self-supervision, but for a completely different problem. So this is just a little teaser, but go read the paper if you want to know more. So reinforcement learning is what you have heard about with all of these things about computers playing video games, Atari video games, right? So basically, you have the computer play, and then as it's trying to optimize a reward, which is like the score of the game, and then it gets better and better and better, and then it beats humans, right? That's the story. But the story here is that these rewards are typically very, very dense. So in Atari games, you have access to the score, and the score is always changing. So you always know how to make it better because it's very local, right? Or sometimes people put little apples in the maze so that you can get a little bit of kind of reward this way. But in many domains, rewards are kind of sparse, right? So for example, if you're playing chess, you only get the reward at the very end. Did you win or did you not win, right? That at the very end of the game is when you get your reward. And so reinforcement learning doesn't really work in this kind of domain. More interesting for me, what if you don't actually ever get a reward? Maybe you're just playing with Legos. There is no desired goal state in Legos. There is no desired outcome. You just want to play. And so that's what we were kind of interested in. And in psychology, it's called curiosity. So curiosity it's argued, is the intrinsic reward that is employed by us humans to kind of bridge the gap between the long-term reward that is eventually maybe coming and what are you doing right now. And so the idea is to try to make an agent use curiosity as well. And this has been looked at in the past a while. And one of the ways that curiosity is defined is difficulty to predict, right? So the idea is that if you know what's going to happen if you do something, maybe it's not that interesting to do it anymore because you already know the outcome. Okay? And so the idea would be, for example, for Mario Brothers, if you press the left button and eventually you figure out that the guy is going to run left, you press right button, it will right, up, it's going to jump, down, it's not going to do anything because there is ground. And so after a while, you're basically going to get bored with this because you're going to know what's going to happen. You're going to have the prediction. But then, when you get something new, and say, wait a minute, I cannot go right anymore. I hit right, but I don't go right. And that makes you curious, and so you want to hang out more around this area and see what else you can learn about this. And then you can make progress, okay? And so the main key to the paper is that we are doing prediction, but not in pixel space. We are doing prediction in the space of latent features that we are learning using self-supervision. But I'm not going to talk about that. I'm going to just show you the video of Mario using no rewards at all. This is just curiosity. He's just hanging around and playing this level. Okay? Now, of course, the interesting thing is what it's going to do on a new level that it hasn't seen before. So this is the test set. And the nice thing is that often it still makes progress, which in robotics is a rare thing when you can actually test on a test set. But sometimes it's not able to do it. Here the level is very different. Black background instead of white. It gets completely confused. But that's okay because in computer vision we know how to do fine tuning, and so we fine tune a little bit, and then it is able to pass a lot of this level. Not all of it, but some long way in this level. And then we can also do this for Doom as well, but I'm going to skip that. Okay? So, in conclusions, the way we deal with computers and the way we program computers is changing. And so, often instead of telling them what to do, instructing them what to do, it's fine. It turns out it's easier and works better to just tell them, what is it that we want to have done. So kind of going up in a higher level of desires. And maybe sometimes we don't even want to tell them that. Maybe we just want them to be curious. So thank you very much.
Okay, we have time for a few questions.
Можно по-русски.
Okay, yeah, there. So maybe, can I ask the next people to queue closer? Yeah.
По-русски можно, да? Спасибо, Алексей,
Thank you very much, Alexei, for a very interesting presentation. I'm not going to lie, I've been reading your article about curiosity-driven reinforcement learning, and they raise a question about what really happens with the agent if, until a certain point of time in the game, he didn't learn sufficient strategy to overcome some special moment, and he gets stuck, he becomes bored, and he doesn't learn anything else. Can you give some ideas and insights how to overcome these difficult problems?
So the question is, when you're doing this curiosity learning, there is this annoying problem that if you are trying to do something, if you don't succeed for a long time, you get bored. So for example, when I was learning how to play the guitar, it didn't sound good for a very long time. And so I stopped doing it because I stopped being curious about it. And this is exactly what's happening in Mario, that in one point, it needs to jump by hitting the right arrow 12 times in a row, which is actually not easy to learn. And so it just tries doing it, and then it just basically learns that it's going to fail, and it stops being curious. We don't know, actually, how to deal with this. This is this probably the right answer is some sort of a hierarchical story where the idea is that you're going to you want to learn some some smaller building blocks that you're curious about, and then put them together into kind of a larger hierarchical stuff. So that's a way to go long distances without really trying it from scratch. So I think that's really the right direction, but we don't actually know how to do it. So I think it's an open problem. We have all the testing code is already online on GitHub, and we're going to post the training stuff on GitHub, I think, in a couple of weeks. So you guys can all just try to see if you can solve this problem.
Yes.
Спасибо огромное за презентацию.
Your presentation. Can you show us an image with Vladimir Vladimirovich?
Я думаю, это просто символ нашей
конференции. It's a symbol of our conference, I believe.
Это на этой самой на GitHub у нас все.
On the GitHub we have all those pictures.
Между прочим,
it's wonderful.
Мы всегда верим, что нам нужно показывать все данные, поэтому у нас на GitHub.
That's why on the GitHub.
Oh, I should talk in English. We believe in showing all data and failures as well as successes. So we posted all of the results that we ran out. So like 10,000 images and results are all online. And so of course I showed you the nice ones, obviously. And even the failures are kind of nice. There is plenty of images for which it really doesn't work. So this is something that, you know, this is not a solved problem. We're still in the beginning stages. So yeah, there is plenty of work to do.
Не, на самом деле я же хотел вопрос задать.
Honestly speaking, I wanted to ask a question related to these. Well, this is clear enough.
Дело в том, что
the thing is that when a person invents an idea, it looks like something that you are showing on the right side of this picture.
Яблочков придумал там.
Яблочков has invented how to generate the curve, then put a wolfram, then a colb, then they made a lamp. Why am I saying that? Things that you are doing right now is a theory of imaging. Why it's not transposed to the space of ideas and bringing up to semantic nucleuses, which makes this the main of industrial processes, the idea of industrial clusters and many other things. Simply speaking, if I have developed an idea, I have patented it and fixed it on the blockchain, why can't we transpose it to the most applicable spaces and dimensions semantic as a semantical core? Thank you very much. And possibly even the error ones.
Okay, okay, this is a difficult to translate question, but I think the way I understand it is that it's if it works for images, why can't this type of thing kind of transfer work for a space of ideas, right? I think the main problem is that the space of ideas is not very well we don't know the representation for the space of ideas. The space of images it's a matrix. It's simple. Space of ideas, who knows? So I think once somebody figures out this beautiful, you know, vector representation of ideas, probably these kind of methods could be tried. But I think the representation is the hard stuff here. This is all quite easy. I think the representation is the hard. Yeah.
Thank you very much for such an interesting presentation. I want to look at and watch it and rewatch it once again. When I looked at this picture once again, I've seen that the leg was not repainted. The right arm is not repainted, but the rocks which are in the background, for some reason they have been repainted into a tiger or a zebra. So the question is, in the following, can we receive this presentation so that before going to sleep I would watch it once again?
So is the presentation going to be available, and looking at some bugs in the failures? So the presentation, I'm not sure if they're recorded or not, but all of the data, everything is online. I think if you Google cycle GAN, you should get all the data, all the images are there, and all the failures you can have access to. Remember that this is, as I mentioned in the other example, it doesn't know what a horse is. It doesn't know what a zebra is, right? It's trying to find some correspondence between two domains. So it's trying to learn the concept of a zebra, right? This is the kind of the self-supervised part. But it doesn't, it might actually not have enough data for that. So it basically probably learns some sort of kind of a zebra-like patterns and horse-like patterns. And so the fact that, you know, the leg here is not colored and the arm here is not colored and the background is colored is probably due to the fact that the texture of those things doesn't look like zebra texture, as opposed to actually finding the full animal. So I think that's kind of the fundamental thing, that you don't actually get the sense, the semantics of the entire object. You just basically, it's still looking at it from kind of a local texture-like properties.
Okay, let's have the last question, preferably not about this zebra. Yes.
Хорошо, по-русски.
Well, I will ask it in Russian. You just told us about possibly that you didn't have enough data. How much data do you think we need to train well
Very good question.
Очень хороший вопрос
о том,
сколько данных нам необходимо для того, чтобы делать эти вещи. И здесь я хочу сказать вам очень такую разочаровывающую вещь. Это массив данных, и вся моя карьера вращалась вокруг сбора больше и больше количества данных. Джон об этом просто жалуется постоянно. Я постоянно думаю, что чем больше данных, тем лучше. Но, к сожалению, это... С Гансом ситуация не такова. Я не знаю, Виктор согласен с этим или нет, но вот эти множество данных, мне кажется, они выглядят очень хорошо. И там всего лишь 400 фасадов, 400 изображений было взято. То есть это маленький объем данных на самом-то деле. И когда для других доменов, когда мы, например, пытались делать нечто подобное, здесь, потому что мы генерируем изображения сами, используя архитектор, мы можем использовать сколько мы хотим. Выясняется, что после определенной...
It actually stops improving and maybe even just makes it even a little bit worse. Other nasty things that happen is that if you train your GAN long enough, it becomes worse again, which is again not true for like a standard neural network. So I think GANs are just very fickle at this point, and I think we just don't know how to optimize them well. I think hopefully a lot of these issues will be solved when we figure out how to deal with GANs better. But right now it's a little bit ugly and embarrassing.
Maybe the very last question.
Thank you for your presentation. My question is, you have two spaces, space of images and space of photos. And if you have image, you have, or if you have a photo, you have much more data. So you have details, you have more information about places. And when you try to encode from space of photos into image, it is okay, you gain less data. And when you try to decode back, you must have some equation because amount of data. And how you beat this problem in your researches?
So it's true that, so it's actually even more complicated than that, because when you have two domains and the sizes are unequal, even if the sizes are equal, we are also seeing that it's always the case that one domain looks much better than the other. So for example, apples to oranges looks generally much better than oranges to apples. And we think that probably it's because here the cycle assumption is that it's a one-to-one correspondence. But of course, it doesn't have to be the case, right? It doesn't have to be one-to-one. And so I think a lot of this is an issue with the domains having different amount of information, and it's also the sizes are also part of that issue, I think. So we usually use more photos than paintings because we just have more photos, but we found that using maybe more than an order of magnitude more doesn't really work that well. We're right now looking at trying to pick and choose which of the photos are more likely to work well with the images. So again, another little story is that when we started, we took the Cézanne images and then we translated them into images from ImageNet or Flickr, and the results looked very bad. And then I thought, but I have lots of photographs of France, and since Cézanne was in France, maybe it will be easier, and indeed it was. So I think there is a lot to be said for choosing the kind of, even if the two distributions are far, you might want to kind of find the closest, the nearest sides of them and do translation in there. That's our hope, but we don't have any results there yet.
Okay, thank you so much.